Now we're going to take a look at some questions based on the theory that we just covered this morning. And these are taken from past papers, so they'll give you a flavour of what's examined and what's asked in terms of heat of neutralisation. I've also put up another 3 questions on Google Classroom they're going to ask you to take a look at. And when we have our live class tomorrow, say 5th year chemistry live class tomorrow, I'm going to go through these questions with you, and I'll take any questions then that are in your heads about any of the thermochemistry that we've covered to date. So this question here: in an experiment to find the value of heat of neutralisation of ethanoic acid, no, just stop there. Ethanoic acid is a weak acid, okay? So straight away we got to keep that in our heads. It was found that when 50 centimeters cubed of a 1 molar solution, now dm minus 3, that's the old-fashioned way to write a litre, okay? We don't use that anymore. We just call it 1 mole per litre, okay? So don't worry about that dm minus 3. So 50 centimeters cubed of a 1 molar solution. Now you've got to think about that, because 1 molar solution means 1 mole per litre, okay? 1 mole per litre. We don't have a litre, we have 50 centimeters cubed. So if there's 1 mole in 1 litre, then surely there would be a 20th of a mole in 50 centimeters cubed, because 50 centimeters cubed is a 20th of a litre. So therefore you have a 20th of a mole. See that? So we know exactly how many moles we're dealing with. That's the key thing in chemistry. And 1 over 20, of course, is 0.05 moles. So this particular question is only dealing with a very, very small number of moles, 0.05. Okay, let's read on. So it was found that when 50 centimeters cubed of a 1 molar solution of ethanoic acid was neutralized, 2.79 kilojoules of heat energy were produced. Now, what they're trying to tell you there is this: when 0.05 moles of ethanoic acid were neutralized, then that gives me 2.79 kilojoules of heat energy. But that is not the heat of neutralization, because the heat of neutralization is the heat change that takes place when 1 mole of the ethanoic acid H pluses are neutralized. So what I have to do now is I have to bring this back to 1 mole by multiplying that side by 20, and likewise I'm going to multiply that side by 20 as well. And when I multiply 0.05 by 20, I get back to my 1 mole. And when I multiply 2.79 by 20, I get 55.8 kilojoules per mole. And that is the heat of neutralization. Now, just a little word here. 55.8 kilojoules, it is not the magic number of 57. And the reason why it is not the magic number of 57 is that 57 kilojoules per mole is reserved only for strong acids and strong bases. This ethanoic acid is a weak base, so we expect the value to be a little less than it would be if it was a strong acid or a strong base. So that is actually in line with our expectations. Okay, what else are we told? When a similar heat of neutralization experiment was carried out using, again, 50 centimeters cubed of a 1 molar solution of sulfuric acid. So now we've got a very, very strong acid. It says 5.72 kilojoules of heat energy were released. Okay, so again we've got to go back and figure out, there's going to be a little change here. We've got to figure out 50 centimeters cubed of a 1 molar solution. What does that mean? Well, that means a 20th of a 1 molar solution, which again is 0.05 moles of H2SO4. Now just be very careful here, because H2SO4 is diprotic or dibasic. It produces 2 H pluses. Okay, so if you have 0.05 moles of H2SO4 and this thing, when it dissociates, gives you 2 H pluses, then the number of moles of H plus will be twice the number of moles of the acid, which is 0.1 moles of H plus. Do you see that? That's very, very important. So it's 0.05 moles of a diprotic acid. And because it's 0.05 moles of a diprotic acid, that means every molecule will give 2 hydrogens. So 0.05 moles of the acid will give twice as many H pluses, which is 0.1 moles of H plus. Now what does that say? Well, that releases 5.72 kilojoules. We have to work out the heat of neutralization. Go back to the definition. It is the heat change that takes place when 1 mole of H plus is neutralized by 1 mole of OH minus ions. Okay, so we've got to bring this back to 1 mole. To get to 1 mole, I'm going to multiply this side now by 10. So I've got to multiply that side by 10, and you'll notice that's 1 mole, as we expect, and 10 times that is the 57.2 kilojoules that we have come to know is the magic number for the heat of neutralization of a strong acid. So it works, okay? But be very careful. Is the acid monoprotic like HCl or HNO3? Is it diprotic like H2SO4? Be very careful with the amount of hydrogens each molecule gives out, because that deviates then the molarity of the H pluses apart from the molarity of the acid. Okay, let's move on. Now, next question here. This is again, I think this can be either last year or the year before, but it goes through the practical, and that's what I want to do with you. I just want to go through the practical to make sure you understand the theory behind it. The cardboard cup with a plastic lid in the diagram contained 150 centimeters cubed of 1 molar hydrochloric acid. So 150 centimeters cubed of a 1.0 molar HCl. Okay, that's a strong acid and it's monoprotic, so therefore the molarity of the acid will be the same as the molarity of H+. We'll just keep that in our heads. A volume of 160 centimeters cubed of 1 molar sodium hydroxide, NaOH, also at room temperature, was added quickly. Now, let's just think about that for a moment. These are added together, okay? There is 150 centimeters cubed of 1 molar acid, and into that is being thrown 160 centimeters cubed of 1 molar NaOH. I hope you see that there is 10 centimeters cubed of base in excess that will not be involved in neutralization. So the 150 centimeters cubed of the 1 molar acid will only require 150 centimeters cubed of the 1 molar base. So there's a bit of a trick in that question, okay? The 1 molar HCl, that's called a limiting reagent because it's present in lower amounts and it will all be used up. 10 centimeters cubed of the base are left over, forget about them, okay? So in that sense, what do we get? This is going to give me 300 centimeters cubed of water because only 150 of each can neutralize one another. Equal volumes of equal strength of equal molarity, see? So it has to be the same. So a little bit of a trick in the question. There are 10 centimeters cubed of base left over that will be swimming around looking for a H plus to bond with that simply won't be there. So we ignore them. So it's 150 of acid will react with 150 of base to give 300 centimeters cubed of water. What are we told next? The temperature of the mixture rose rapidly by 6.4 Kelvin. Now look, rises in Kelvin and rises in Celsius and centigrade, they're exactly the same. So therefore we've got theta is equal to 6.4 and then began to fall gradually. Okay, so now we've got our water volume, we have our rise in temperature theta, and we're also going to be told later on what the specific heat capacity of water is when we're asked to do the calculation. So let's move down through the questions that are up here first of all. The equation for the neutralization reaction took place is HCl plus NaOH gives NaCl and H2O. Now that's the typical neutralization experiment. Notice the acid and the base give water. They will only form the salt fully when the water is evaporated. So at the moment, the Na and the Cl, they're in aqueous solution. That's why it has an AQ at the bottom of it. Okay? Is this reaction exothermic or endothermic? And justify your answer. Well, go back here. What does it say on this line? What does that line say? The temperature of the mixture rose. So if something gets warmer to the touch, it's obviously exothermic. And that's all you've got to say. It's exothermic because there was a rise in temperature. And if your thermometer registers a rise in temperature, something is giving out energy. So that's exothermic. Part B. Why should the mixture be stirred before taking temperature readings? Well, you're adding two liquids together. Hopefully, you have got both of them to the same temperature. But when you're adding them together, you have to homogenize the solution. You've got to mix it to make sure that the temperature is uniform throughout the entire solution. Part 2. Suggest a reason why the temperature having risen then began to fall gradually. Well, the same thing is what happens when your fire goes out. When your fire is burning, you get heat. As soon as the fire goes out, it begins to drop because it's cooling down. it's losing the energy to the system. It's exothermic. So it's giving out energy. When the reaction is over, it cools down. It continues to try and heat the universe, which it's not going to do. So therefore, it cools down to room temperature. Part 3. The thermometer used was accurate to 0.1 Kelvin. What temperature rise would have been recorded if the thermometer was used accurate to 1 K? Now this is asking about rounding off. The thermometer that's used was accurate to 0.1, so that gave me 6.4. But if my thermometer was only accurate to 1 K, then you'd have to round off to the nearest K, which in this case would be 6. Okay, so that would be 6K if it was only accurate to 1K. But because it's accurate to 0.1, it's far more accurate. That means it's accurate to 0.1 of a tenth of a degree Kelvin. So therefore, 6.4 is what gives us there. Part C. Why is it advantageous to use moderately concentrated solutions instead of dilute solutions in this particular experiment? So why is it advantageous to use moderately concentrated solutions instead of dilute solutions in this experiment? Well, if we're using dilute solutions, it's too much water. So if we're using moderately concentrated, that means there's a good amount of acid in there, meaning a good concentration of H+, and again, with the concentrated base, a good concentration of OH-, and that's what you're measuring. You're measuring neutralization, so therefore you want to get as many H pluses and OH minuses to come together as you can, hence the reason why they should be moderately concentrated. Concentrated means a lot of chemical in a particular area. Draw or describe, now in a situation like that, I would do both, okay? Draw or describe the hazard warning pictogram that should be displayed on a container used to store 1 molar NaOH. Now, if your artistic skills are as good as mine, then you know that it is, well actually it used to be a square, they've changed them now, they've actually changed them to diamond shapes. So we better do that, because we don't do the diamond shape, it'll show we haven't caught up with the present day. And then you have drops on a hand, so you've got a hand like this, there's a thumb, there's the fingers, something like that, yeah. And then you have a bench, like that. And on the bench, there's a corrosion there, and there's corrosion here, and then there's drops falling on it, something like that, yeah. Something similar to that, which means it's corrosive. Now, you may also say in English, the pictogram would represent a hand and a bench being corroded by a liquid that's falling on them. So it's corrosive is what you're looking for. C-O-R-R-O-S-I-V-E, corrosive. Okay. And that's part C. Okay, so draw or describe that picture, that pictogram. So look, if your drawing is better than mine, which it probably is going to be, then you draw the picture and you give the name. I would always do both. If they tell us to do one or the other, do both. You're guaranteed to get full marks if you're able to do it that way. Okay, let's move on. Now, part D. Calculate the number of moles of HCl neutralized in the cardboard cup. What were we told? We were told it's 150 centimeters cubed of 1 molar HCl. So let's just write that down here. It's 150 centimeters cubed of 1 molar HCl. What does that mean? 1 molar HCl means that there is 1 mole in 1000 centimeters cubed. But we didn't use a litre, and we never use a litre. Instead, we used 150 centimeters cubed. So therefore, we're going to take 150 divided by 1000 to work out what the number of moles is here, and it's 0.15 moles. Okay, so 0.15 moles. That's what you're dealing with. All right. So that's the first part done. Part 2, the heat produced by the reaction. Now stop there for a moment, because just let's think back to what we did in part 1. The heat produced by the reaction is the heat that is produced by only the 0.15 moles that we have used. So we're going to have to do a little bit of building up, bringing it back to 1 mole when we're finished at the end of this. So the heat produced by the reaction mixture that had a total mass of 310 grams, taking the specific heat capacity of the mixture as that of water, 4.2 kilojoules per kilogram per Kelvin. That's what they wanted to calculate. So sorry, calculate the heat produced by the reaction mixture that had a total mass of 310 grams. Now, that's a bit confusing, because in the previous part of the question, they told us that 150 centimeters cubed of acid was mixed with 160 of base, which leaves 10 centimeters cubed of the base outside. But here they're telling you it has a total mass of 310. Okay, so the heat produced by the, calculate the heat produced by the reaction. That's the formula, E equals mc theta. Okay, so we're going to use that formula. Now, what do we need? We need we need m in kilograms. So just keep in mind, they're quite pedantic. M is in kilograms. There's 300, you have to take it to give you the question. There's 310 grams, so that's 0.31 kilograms, multiplied by the specific heat capacity, 4,200 joules. And by the way, C must be in joules, not in kilojoules. Okay, and the rise in temperature, we were told, went up by 6.4 Kelvin, which is the same as 6.4. A rise, it's the same as a rise in 6.4 Celsius as well. So let's multiply those out. 0.31 multiplied by 4,200 multiplied by 6.4 works out as being 8,332.8 joules. Okay, but that's 8,332 joules for that particular reaction. So in other words, that is part 2 finished. Okay, that's the answer to part 2. But you keep in mind that that is the energy that has been released by only 0.15 moles. Look at part 3. Part 3 says, to 1 decimal place, calculate the heat of reaction. What's the definition first? The heat of reaction is the heat change that takes place when 1 mole of H plus ions, so there, just stop there, 1 mole of H plus ions. We don't have that. We're told 0.15 moles gives us 8,332.8 joules. So what I want to do is I want to go to 1 mole. And the quickest way to get to 1 mole is to divide both sides by 0.15. So when I divide that by 0.15, I end up getting 55,552 joules. Now, what did we expect? We expected 57,000 for the very simple reason that we were using strong acid and strong base. So we expected 57,000. We didn't get it. We're working in a second level laboratory. We're never going to get 57. We'll get close to it, okay? But that's what we got. We got 55.552 kilojoules per mole. That's the answer to part 3. And lastly then, part E, which is always going to be asked. The result obtained was about 3% below the expected value. Happy days. We're right then. We get 55 because we're below the 57. State and explain a modification to the method described that would give a more accurate result. Okay, number 1, you get your volumes right. You put in 150 of both. Make sure they have the same molarity and they are both strong acids and bases. Okay, so make sure first of all the volumes are correct. That's 1. Number 2, make sure that when you take the reading, you do so as quick as possible. So when you're taking the thermometer, you do so as accurately as possible. So therefore you could use a digital thermometer rather than one that is used with using your eyes to measure. Okay, so number 1 would get the volumes right. Number 2, you could use a digital thermometer for more accuracy. And number 3, what do we think? What's the third one we could do? A modification. Is there a lid on that cup? Let me just see. Is there a lid? Oh, there is. Okay. So that's it then. That's basically it. Use a digital thermometer. Make sure you get your volumes correct. Oh yeah, and of course, the most important thing, before you add the two together, make sure they're at the same temperature. So there's 3 things you could give back. You're only asked 1 modification. So you could say, get the volumes correct, number 1. Number 2, you could also say, use a digital thermometer instead of a glass one for more accuracy. And number 3, make sure that the liquids, when you're adding them together, are the same temperature. All right, that will make it far more accurate in terms of being able to detect and measure a heat rise. So look, that's it. That's the question as it's asked. So I'm going to leave you now with the 3 questions that are on Google Classroom. Tomorrow we'll have a live class and then we'll go through this again. I'll take your questions or any calculations that you want me to go through and I'll do them with you.